Thanks again, everyone, for joining. I'm Bret Stonebridge from Radiant, and I'm happy to be your host today. In this webinar, we're going to discuss regulations surrounding replacement of mirrors throughout the vehicle and step through the recommendations in the newly issued SAE standard for testing display-based systems. By the end, you should have a good understanding of the current state of mirrorless vehicles in the U.S. and how you can apply testing system advantages to fast-track your CMS development. First, to introduce Radiant Vision Systems. At Radiant, we specialize in imaging for light and color measurement, and we've been manufacturing scientific-grade automated measurement systems for over 30 years. Our solutions are designed for automated visual inspection throughout manufacturing. We support a global customer base with direct offices in the US, Asia, and in Europe. Each year, we implement thousands of Radiant systems, inspecting millions and millions of devices to ensure absolute product quality. Today's webinar will cover topics on regulations surrounding vehicle mirrors and rear or indirect visibility, CMS or camera monitoring systems that are only just beginning to be applied in place of mirrors throughout the vehicle, current standards that define minimum visibility requirements of mirrors and performance expectations for CMS to provide equivalent visibility, the UN standards, as well as upcoming requirements for the US and Canada. In particular, we're going to walk through new SAE J3155 test protocols and recommend test systems with advantages for evaluating aspects of a CMS display, such as image quality, depth of field, color rendering, directional uniformity, and a few others. All right, so mirrors have been standard vehicle components since the mid to late 1960s, which is when we started to see an increased safety standard around indirect visibility. For several decades, side and rear view mirrors have been mandatory in the vehicle interior and exterior. In the past few years, mandatory vehicle mirrors have been targeted for replacement by display-based systems in both passenger and commercial vehicles. Because of these existing regulations, standards organizations and governing bodies are now looking to regulate the visual quality of the display used for indirect visibility. So, as display-based systems are introduced, the regulations governing current mirror or mirror rear visibility systems are being extended to include display performance requirements. Already, global standards are being rolled out for display-based systems in countries that have legalized mirrorless vehicles, as well as those who are anticipating them. For example, rear visibility regulations such as UN 46 and ISO 16505 standards for the UN and other contracting parties or countries are already adopting these standards. We also have FMVSS number 111 in the US and CMVSS 111 in Canada. And we actually already have a few examples of this in the market. One of the first commercially sold vehicles to incorporate a mirrorless design was the Lexus ES, sold exclusively in Japan, where mirrorless vehicles were first approved. So what we can see here is a camera system that has replaced the side view mirror and a display mounted on the inside door panel to show the live camera feed. Alongside Lexus, Audi's 2019 e-tron was another to first feature a mirrorless design and was sold into Europe. What we can see on this PowerPoint here, this example is a video showing a e-tron Sportback, again with the camera replacing the side view mirror and a display embedded into the door panel. Gradually, we've seen more traction on mirrorless concepts since these models were introduced. Just a few months ago, Sony and Honda announced a partnership in EV development. Here we have an image of Sony's initial mirrorless concept, the Sony Vision S. The SUV version of this concept was just debuted at this year's CES, but is still in the R&D phases. Camera and display systems that are being used to replace vehicle mirrors have gone by several different names. The technical term for these systems is camera monitoring system, or CMS. This terminology is used in documentation by governing bodies such as the UNECE and NHTSA or NHTSA, and referenced by standards documented from ISO and SAE. However, in the market, CMS has also been referred to or branded as virtual mirrors, in like Audi's example of the virtual exterior mirrors, or digital mirrors. And an example with this would be the digital center mirror or digital side mirror in the Honda Ioniq 5, or even e-mirrors, sometimes used by CMS systems manufacturers like Faurecia or Forvia, with their e-mirror designs shown in this image on the right side here. So there's a few different names, but we're going to be referring to CMS as we go through this presentation, just keeping it collected. And this is really just the beginning. There's a lot of room for this technology to get really creative. As just an example, BMW has filed a patent with the EPO in 2021 defining a kind of HUD mirror. This incorporates a display substrate into the driver's side window to stream content from an external camera, eliminating the need for another display component within the cockpit. So regardless of how mirror concepts are integrated, they offer a range of benefits for side and rear visibility, especially considering some of the advantages of using a display. For instance, to improve situational awareness, displays can provide an unobstructed view of the exterior without the usual blind spots. And a camera and display can also theoretically capture a larger field of view than a conventional mirror, increasing the scope of visibility for the driver. These systems also improve the general clarity of objects. Digital images can be rendered in various ways to enhance brightness, color, and contrast, and these systems can also be designed to reduce glare from headlights or maybe even ambient light as compared to harsh reflections that impact conventional mirrors. Apart from enhancing visibility and providing new design opportunities, removing mirrors from the vehicle can also improve ergonomic comfort, reducing the driver's head and eye movement to view different mirror locations. And mirrorless vehicles provide reduced air resistance on the exterior, meaning improved aerodynamics to reduce overall fuel consumption. For example, this image comes from the study by Exacorp several years ago, who concluded that the average car burns 1 tank of fuel every year due to the external mirrors alone. So because of their importance for vehicle safety, there are strict regulations surrounding devices used for indirect and rear visibility. Currently, regulations on integration and performance of conventional mirrors set the bar for any other system used in their place. In the European Union, UN Regulation 46 provides the uniform provisions concerning the approval of devices for indirect vision and of motor vehicles with regard to the installation of these devices. For the US and Canada, there are roughly equivalent regulations in the Federal or Canada Motor Vehicle Safety Standards, or FMVSS or CMVSS 111, which set minimum requirements for rear view mirrors to provide drivers with a view of objects that are at their sides or to the side or rear. These standards have defined specific types of classes of mirrors that all vehicles must have. In the US and Canada, required mirror types are referred to by their location. For example, a driver's side outside mirror or an inside rear view mirror. In the UN, ISO standards have classified mirrors from class 1 through 6 for passenger and commercial vehicles, as shown in these images. For passenger vehicles, there are 2 required mirror types for side and rear view visibility. The blind spot is much smaller for smaller cars, so we need fewer mirrors for full visibility around the vehicle. Looking at mirrorless vehicles, we can improve our rear visibility for passenger cars when displays are used. This is because blind spots can be theoretically completely eliminated. In commercial vehicles, we have much larger blind spots due to the vehicle size itself. So there are several more mirror classes governed by the commercial vehicles to ensure full visibility around the vehicle. Classes 2 through 4 mirrors provide rear visibility in commercial vehicles, making them a primary focus for replacement by display-based systems. But other ground and side visibility systems are also being considered here. Because mirrors are so strictly controlled, replacing mirrors with a display-based system must first be approved by governing organizations and incorporated into automotive safety standards. Updated documentation is needed to address installation and performance requirements that ensure new vehicles provide the same level of safety as conventional mirrors for rear visibility. So in the EU, the UN ECE governs automotive regulations for the automotive industry. In November 2015, under UN Regulation number 46, Addendum 45, the UN ECE approved the use of display-based system as an alternative to mirrors for the first time. This change permitted the replacement of Class 1, 2, 3, and 4 mirrors. This change to UN 46, R46, relied on newly required tests and procedures made available in the ISO 16505 international standard to ensure the performance of these particular display-based systems. Only UN ECE contracting parties or countries who adopt this standard are permitted to replace these mirrors with displays. And so far, like I mentioned previously in this presentation, there's only a few actual mirrorless models we've seen on the road. In the United States, and by extension Canada, we're not quite there yet. The NHTSA governs vehicle safety in the US and has been reviewing the use of display-based systems in place of mirrors for several years. The latest movement was a participation study conducted in April of this year to collect data and comments from people operating mirrorless vehicles in test environments. But so far, the outcome is still TBD, to be determined. But it's clear that this industry sees the change in terms of when rather than if. So manufacturers of display-based systems have already produced several concept designs and must get ready to meet those coming requirements. These mirrorless systems would be regulated under FVMS 111, which specifies requirements for current conventional mirrors as rear visibility systems. A newly issued document from the SAE is the latest big step forward here. The SAE J3155 Recommended Practices provide camera monitoring test protocols and performance requirements for display-based systems intended to replace mirrors. This document specifies supports FMVSS 111 in the US and incorporates many of the established test methods and standard practices of the existing 16505 and UN R46 documents for display-based system specifications and performance. We'll dive into the new SAE standard in a minute, but before we do that, let's get a little more familiar with exactly what CMS or camera monitoring systems are and how they're integrated in the vehicle. So, by definition, a camera monitoring system is any camera and display system used to enable or improve indirect visibility, usually to the side or the rear of the vehicle. Here, what we can see is the typical integration areas of CMS components, but there could be many more, actually. The classic CMS will provide cameras in place of the side mirrors and usually camera on the front and rear of the vehicle. Inside the vehicle, displays are typically located where the driver is accustomed to looking. For example, we're used to looking up in the conventional rear view mirror location and toward the side view mirror locations at either door. However, with all these new vehicle models, we see the dashboards and other center consoles are slowly becoming the primary visual portal to all aspects of the vehicle. So we could see a display or visibility system centralizing there eventually. A CMS has a few different components to enable operation. First, we have the image or scene that the CMS is capturing to be relayed to the driver. The CMS camera could be a side view or a backup camera installed somewhere on the exterior of the vehicle. Once this camera captures an image, the image is processed and relayed in a live feed back to the CMS monitor, so it's a different component, which is a display screen installed somewhere inside the vehicle. Even though it's not legal in the US to replace the side mirrors using CMS, it's probably likely that you are using a CMS in your vehicle. Backup cameras are a type of CMS that's been required in all new vehicles manufactured in the US since May 1st, 2018. So literally all new vehicles will have a CMS. Just like mirror replace systems that, may be legalized, backup camera CMS are also regulated by FMVSS 111 for rear visibility. A CMS is currently required in addition to mandatory conventional mirrors in US vehicles, but it can't replace them quite yet. That's because we can't do the NHTSA aspect of that testing, which approves the CMS as a mirror replacement. So for now, CMS for mirror replacement is still under review. But because it's still under review doesn't mean that we shouldn't get ready for it. So that's exactly the reasoning behind the new SAE standard document, which provides recommended practices for testing CMS performance, specifically in support of requirements in the US. So first off, what is SAE J3155? Well, this is the standard that recommends practice containing camera monitoring system test protocols and performance requirements. It requires the latest testing requirements for CMS and was most recently issued in December of 2021. And to quote the standard, this SAE recommended practice provides test protocols with performance requirements for camera monitoring systems to replace existing required inside and outside testing for rear view mirrors for US market road vehicles. This practice expands specifically into the content while retaining harmonization with the FMVSS 111 rear visibility standard and other international standards. Following existing CMS performance documentation, the SAE standard incorporates test protocols and test setups for both ISO 16505 and UNR 46. While all CMS must meet the visibility requirements of FMVSS 111, SAE J3155 is just one set of test protocols manufacturers can choose to apply when developing CMS for mirror replacement. SAE's rationale for issuing test protocols speak to the anticipation of CMS approval of mirrorless vehicles in the US. SAE J3155 states, increased demands for occupant safety and fuel economy have reduced rear visibility because of higher belt lines in recent vehicle designs. At the same time, technology improvements in automotive cameras and displays now make real-time camera monitoring systems a realistic option to replace mirrors and potentially improve rear visibility and reduce wind drag that results from exterior mirrors. The purpose of testing a CMS is to ensure that it meets the minimum requirement for visibility and enforced for conventional mirrors. These requirements are specified by FMVSS and ensure rear visibility systems provide adequate field of view and clarity of areas and objects surrounding the vehicle itself. SAE J3155 is broken down into two main sections. The first, section 4.1, covers testing for what's called driver vision. These are vehicle performance tests regarding physical specifications of the CMS and of the vehicle. These tests are used to primarily evaluate the CMS technical specifications and installation to ensure requirements are met for field of view, image size, and driver ergonomics. Section 4.2 covers testing for what's called system design. These are laboratory performance tests regarding image rendering and visibility of the image on CMS display screens. These tests evaluate the quality of the image displayed on the CMS monitor, including properties of the display, time-based properties of the video feed, effects of ambient lighting as captured by the camera, and properties of the display component that impact visibility of the image on the screen. I just grab me some water real quick. We'll assume in this case that our CMS has accurate technical specs and is installed correctly. So we're going to focus on the section about system design and ensuring the best image on the screen. System design testing is broken into 4 sections in the SAE standard. First, we have image quality. These tests evaluate the visual quality of images on the display, including the uniformity, the color, contrast, resolution, sharpness, distortion, and there's a few more. The next being time behavior. And time behavior is testing the live feed impacted by the display and the camera response. Includes tests for frame rates, image formation time, and system latency. The third is the artifact tests, which evaluate the ability of the system to render clear images when external lighting is entering the camera, such as a headlamp from another vehicle. This includes testing for visual qualities like blooming, lens flare, smear point light source effects, and the impact of flickering light sources. The fourth and last category is testing for durability and ergonomics. These tests evaluate physical properties or components of the display that can impact visibility, for example, its general durability, and maybe even glossiness or glare from the glass itself. For the purpose of this webinar, we're going to walk through several test protocols that are being used to evaluate the performance of the CMS display. In the end, we'll provide some recommendations for performing these standard tests using today's available display test equipment. One second. There we go. The first set of tests for image quality evaluate several visual properties that can be influenced by the CMS display or the camera. The SAE documentation specifies that these aspects should be tested. Uniformity of the display, including both lateral and directional uniformity, the luminance and contrast rendering of that display, color rendering of the display, grayscale rendering, resolution, sharpness, depth of field or sharpness as object's distance change, and geometrical distortion of the image in the display. So we're going to walk through all of these, and we'll provide an example for each one of these tests performed by one of the Radiant systems here. First off, image quality and lateral uniformity. The lateral uniformity tests look at the changes in brightness or luminance across the display in X and Y directions. This evaluation is done from a perpendicular view at the center or 0, 0 coordinate of this display. So in this image, we can show a display with general uniformity issues where a false color scale is used to represent the luminance values. So that's what you're seeing here on the screen now. The black areas are lower luminance, the yellow, red, white are higher luminance. Again, this is a false color scale. For the SAE lateral uniformity test, 9 points must be measured across the display, and deviations must meet specific tolerances, as shown in this image. SAE refers to the same test within the ISO 16505 standard to provide acceptable deviation percentages and luminance between points of the display. The next test is the directional uniformity test. The directional uniformity test takes into account the angular dependency of a display brightness or luminance. In this test, the uniformity of the luminance of the display is measured at different viewing angles. These angles represent how the display may be viewed off. Angle, for instance, if you were looking at the display 10 degrees off from particular, 20, 30, 40. But in this image, a false color representation in a polar plot shows how the luminance changes as the viewing angle becomes more extreme in the horizontal or vertical directions. The farther from the center, the more off angle we should be viewing the display. Again, SAE refers to test methods in ISO 16505 for acceptable deviation percentages here. This test, the luminance and contrast rendering, uses a checkerboard pattern to test contrast based on the highest and lowest luminance values. This testing ensures that the minimum contrast of the monitor, including any screen protector, falls within specific ratios under a range of daylight scenarios. For example, for a day condition with diffuse ambient light, SAE specifies that the contrast ratio for brightness of light areas in this image to dark areas in this image must be at least 3:1. Again, SAE refers to 16505 for the specific test setup, including light sources used to create ambient lighting scenarios. The color rendering test evaluates specific hue angle ranges actually, of the display against CIE 1976 color coordinates. Here we show an example test image displayed to measure red, green, blue, yellow, and white. According to the SAE test protocol, each colored square must be measured within specific ranges on the CIE 1976 color chart, uniform color spaces, in the chromaticity diagram. And for those unfamiliar with this 1976, this is the 1976 space and the hue angles defined by SAE J3155 and ISO 16505. This image comes, again, directly from that ISO standard. SAE and ISO documentation has specified that amber, blue, and red light signals displayed on the screen should also be distinguishable from each other. For instance, emergency vehicle or police lights. SAE test methods for color rendering are again conducted according to 16505, that ISO standard. Now, grayscale rendering evaluates what's called the tonal range of the display. In other words, can the monitor produce at least 8 distinguishable gray levels or tonal steps? SAE states that a CMS must have sufficient grayscale rendering according to the method given in UNR46. Both SAE and ISO reference this method. In UN46, tonal difference is defined by a lightness difference using the CIE LAB color space, where L star would need to be equal or greater to the value of 3. Now, this specific test setup can be found in UNR46 Annex 12 for those that are interested. A resolution test evaluates the clarity of these images as they are displayed across the screen. In this case, a hyperbolic wedge or line pattern is used to measure frequencies between dark and light bands. According to SAE, resolution is tested using a measurement of MTF10. So MTF is modulation transfer function and measures the relative contrast at a given spatial frequency, which is key for measuring the image sharpness. MTF10 gives a measurement at a cross-section of the image, as circled here, I see them in the middle there, where lines are positioned at such a distance that spatial frequency differences between the peaks and valleys is 10%. To test resolution, the SAE protocol specifies testing MTF10 in the horizontal and vertical line directions to meet minimum tolerances at the monitor center and at the corners. As a point of interest, FMVSS 111 testing is typically done using a high-resolution digital photometer camera. Actually, a photography camera, However, this equipment has been shown to be ineffective for resolution and other MTF testing for evaluating the image quality of CMS displays. Here are the results from a study performed by SAE for defining of MTF10 test methods for resolution. A digital camera produced inconsistent results when attempting to define the 10% frequency difference at various scales of the line pattern due to different image post-processing. Therefore, the SAE J3155 testing follows ISO 16505, which in turn requires using a calibrated luminance measuring camera, such as an imaging colorimeter, to find the correct 10% or MTF10 measurement point in the test image. This equipment is very common for display testing in general. The sharpness test in SAE relies on a measurement for MTF50, or an area where spatial frequency of the image differs by 50%. Like the resolution test, the sharpness test aims to evaluate image clarity. According to SAE J3155, sharper images enable faster perception of the content shown in that image. Sharpness is tested in horizontal and vertical directions at the center and corners of the display screen. In this case, we use rectangular evaluation areas and measure along each perpendicular edge. This method also follows ISO 16505. According to SAE, the CMS must allow the driver to clearly perceive any objects or content in a captured image at a range of depths. The depth of field test measures the MTF10 at different object distances. This test gives minimum resolution specifications based on 3 distance points. So first we have 10 meters representing infinity. The second we have 6 meters representing the middle distance. And the third being 4 meters representing a closer distance. As stated by SAE, the main focus of the depth of field evaluation is to measure the CMS capability to recognize objects at any distance within the required field of view. The last image quality test in SAE J3155 is the geometric distortion test. This gives protocols for testing the distortion of images displayed on the monitor, which is usually caused by the CMS camera lens. So according to the SAE, the maximum distance of the driver's side display and inside rear view display in passenger vehicles or main view display in commercial vehicles must be measured not to exceed 20% relative to a perfect rectilinear or pinhole projection. In other words, the deviation from a perfect checkerboard pattern. This test method for geometric distortion is provided by 16505 as well. Another category of system design testing in SAE J3155 is artifacts. In this case, the display needs to render scenes while light from external sources enter the image. For example, when bright headlights are shining into the CMS camera. The impact of these light sources can cause visual artifacts such as blooming, lens flare, and or smear. The display must be tested for its ability to mitigate these artifacts as well as produce high quality images where point light sources are flickering and are clearly discernible. The blooming and lens flare test measures the percentage of the image that is visible on the display regardless of bright light sources entering the camera lens. The SAE states that these artifacts should not cover more than 25% of the displayed image. And we're seeing a theme here. This test is conducted according to ISO 16505. Headlamps are a great example of point light sources. These 2 light beams can be captured by a rear-facing CMS camera and must be rendered appropriately by the system. According to SAE, the display should be tested to ensure that the point light sources or proximal light sources are clearly distinguishable by the driver. This test relies on methods from UN R46, which measures a unique value, either point light source detection factor, or PLSDF, or point light source contrast factor, PLSCF, with minimum tolerances. This test is performed using a set of lamps shining into the CMS camera from a specified distance. The test also relies on luminance measurements at various points across the silhouette of a rendered image, like the combined shape made by these 2 light sources that you see in the image here. And this test method follows UN Regulation 46. Okay, so the equipment used to test the visual performance of the CMS can make a big difference when it comes to optimizing the speed and ease of meeting requirements. In this section, we'll discuss test equipment and give some recommendations for optimizing the display test process. We've looked at these components of the diagram before, which make up the camera monitoring system, including the CMS camera and the CMS display monitor. Now, we're adding additional core components of the CMS development process, which is the CMS display test system. This test system includes another camera, which is the inspection or measurement camera, and the software used for image processing or analysis. How the process flows is from left to right. A test image specific to the test protocol being performed is set at a specified distance from the camera in the test environment. The CMS camera captures the image is processed, and then relayed to the CMS monitor. The measurement camera captures an image of the monitor displaying the test image, and then this produces a measurement image of the display that is analyzed by the measurement software. So kind of a longer path there. There could be other components of the test setup as well. For instance, we discussed testing artifacts like blooming and lens flare that are caused by external light sources. Here we can see an example of how lamps are used to create various ambient lighting conditions to perform testing for specific parameters. Lamps used to illuminate the test image can create different daylight conditions from a bright day to a night, use D65, and there's other examples as well. High intensity lamps can be used to emulate headlamps or other bright light sources. And then finally, a mirror could also be used to directing high intensity light towards the camera to maybe emulate sunlight as an example. Here's a visual example of just one kind of test setup using these components. Both images are showing the same test setup. One is from the side and the other being a top-down view. In this case, the setup is testing the CMS that is being used to replace the passenger side view mirror. A test pattern of a checkerboard is propped up on an easel where diffuse lamps are pointed to illuminate the pattern, and this pattern is captured by the side view camera mounted on the car. Then the camera feed is relayed back into the vehicle monitor, which is being tested outside the vehicle on a tripod. A measurement camera is on one other tripod facing the monitor and capturing an image of the monitor to evaluate display quality. Most likely, we're testing the luminance and or contrast rendering performance of the CMS as an example here. Within the SAE standard and the referenced ISO 16505 test methods, test equipment is described as requiring certain capabilities to ensure the reliability and accuracy of test data. Test protocols in SAE recommend testing the CMS display using a calibrated luminance meter or a luminance colorimeter. This kind of system can measure spatial luminance, which is in turn measured in candela per meter squared, and absolute color values measured in CIE chromaticity, whether that's 1931 or 1976, XY, U prime, Z prime color coordinates. Because so many contextual analyses are needed to perform standard-based CMS testing, we also need an imaging system. A contextual analysis using an image can use two or more measurements from many points on the display to compare differences such as contrast from dark to light regions or maybe uniformity from center to corner as an example. To meet these specifications for SAE-based CMS testing, an imaging colorimeter is going to provide some huge advantages here. This is an image-based measurement system that specifically measures light from images. It captures light by mapping received photons to relative locations on an internal image sensor plane. Using internal color filters and unique calibrations, imaging colorimeters measure brightness and color according to standards set forth by CIE or the International Commission on Illumination. These include luminance values and absolute CIE chromaticity values, which are universal for display measurements. Earlier, we referred to a study that looked at the effectiveness of measuring MTF for resolution. The result concluded that a calibrated luminance measuring camera, such as an imaging colorimeter, was necessary. As proven in the study, and due to requirements for photopic measurement values, any device that does not measure absolute light and color will not be practical in CMS testing. And any device that doesn't capture images of the display for analysis is not going to provide efficient evaluation. So that leaves us with the best option being a colorimeter imaging system. Several protocols in SAE standard CMS testing require several protocols in SAE standard CMS testing require an MCF test using a hyperbolic wedge test image. In this depth of field test, the MCF value is captured for images positioned as far away as 10 meters from the CMS camera. A CMS display has an MCF value, but so does the camera being used to measure that display. Accurate measurement depends on isolating the MTF to the CMS itself. We don't want the optical specifications of our measurement camera to introduce its own poor MTF and cause false defects because we are unable to capture a clear measurement image. This can become even a bigger problem. The farther the CMS camera is from the test image being captured, because resolution of the lines in a hyperbolic test image are quickly blurred due to the CMS camera resolution. So this is especially an issue in depth of field testing that we see here. To meet specifications for accurate depth of field and other MCF testing as part of SAE test protocols, the resolution of our measurement camera must be sufficiently high. With high enough resolution, we can eliminate any effects from the measurement camera in the image of the display we are capturing for analysis. This means that any issues we measure are isolated to the CMS camera and the monitor itself. A recommended measurement resolution is 3:1. Test camera resolution versus the CMS monitor resolution. As an example, a 29 megapixel or higher resolution system will likely optimize measurement performance in most settings and reduce the risk of error. What we can see in these two images is we can see the visualization and the difference between two different resolutions. The fewer measurement pixels we apply to the image of the CMS display, the harder it is to tell if the CMS has poor performance or if it's just our measurement system. With a high resolution measurement system, all of the CMS display pixels are fully resolved, so we can isolate resolution issues to the CMS itself. When it comes to testing color, SAE specifies the CMS monitor must be tested based on CIE U prime V prime values. And as we saw earlier in the color rendering test protocol, the CIE 1976 uniform color space is used. So with hue angle tolerances provided by 16505 and R46 for red, blue, green, yellow, and white. A color measurement system designed to measure color per wavelength based on standard CIE color matching functions is really what's needed to ensure we're accurately calculating that 1976 CIE U prime V prime color coordinates. This kind of system weighs wavelengths of light entering the camera's lens using optical filters that match CIE tristimulus curves shown here. Now these curves model standard human visual perception of color and allow universal values to be calculated. With these optical filters and color calibrations applied, an imaging colorimeter like the Prometric I series from us at Radiant show here capture accurate and repeatable measurements of color according to the CIE and the outputs according to the 1976 color space. These systems can capture and calculate millions of data points in a single image in seconds, ensuring each region of the CMS display is accurately and efficiently characterized against the necessary tolerances. For directional uniformity testing, the SAE requires that the luminance differences across a CMS display be evaluated at a range of viewing angles. The visibility of images in a display for different lighting conditions is greatly affected by the viewing direction or angle. For example, a fixed integrated display in the interior of the car is typically viewed off angle. This could be a virtual mirror above the driver's head. It could be a display panel to the left-hand side of the door. It can be many different things. But SAE J3155 tests directional uniformity using methods outlined in 16505. This requires testing luminance at 9 different points on the horizontal and vertical locations of the display, perpendicular to its orientation. So according to 16505, measurements are made by using a goniometric system or a conoscopic measuring system or something of equivalent there. The key is that each point must be measured at each orientation to meet precise luminance tolerances. One way to measure a CMS display directional uniformity at various viewing angles is to position the display and use a measurement camera at different physical angles of rotation relative to one another. This is the goniometric approach. A goniometer is an instrument that rotates a piece of equipment, for instance, a camera around the display. The problem with this method is just how long it takes to capture each point at each rotation, repositioning equipment every time, capturing several images, and then comparing them. It's very, it's not an efficient way of testing this. Also, without any moving parts, there's a risk for error. If the appropriate angular rotation isn't achieved, or if one component is misaligned from the other, there could be inaccuracies in the measurement and the solution. A much more efficient solution is actually using a conoscopic lens. A conoscope lens enables a photometric imager like the one in this image to capture a full cone of light emitting in angular space from a single point on a display. The angular light entering the measurement camera lens is transformed to be captured in a 2D image by the camera's sensor. So here, this is an image captured by Radiant's conoscopic lens solution, which allows a polar plot of light from a display emitted in angular space. The difference in luminance values are shown using, again, that false color scale. So this system can measure out across plus or minus 70 degrees, where values farther from the center of the image here are at a higher degree of rotation from a 0-0 perpendicular position. This image is captured in a single shot, so all directional values can be measured all at once. The complete analysis just takes a few seconds, significantly shortening test time versus a goniometric system shown previously. While there are many other system advantages we could describe with respect to time, we'll kind of wrap it up here today. But to summarize, we're on a fast track forward to implementing of CMS in place of mirrors, with Japan, Europe, and others already implementing systems. The US and Canada are definitely not far behind here. And with recent test protocols from the SAE now supporting the standard rear visibility requirements in the US and Canada, manufacturers can start to look more seriously at designing the CMS that have practical future applications. Those looking to get ahead of the market really need to consider the advantages of testing equipment to fast track their CMS components for rear visibility compliance. As an example, photometric imaging systems for accurate light measurement data and fast, comprehensible analyses, high-resolution cameras for accurate MTF measurements, especially at a range of different object depths, the CIE matched color measurement systems to evaluate colors rendered on the display and against tolerances mapped out in the 1976 color space, the angular measurements of the conoscopic solution capable of measuring all test points required for directional uniformity or a view angle one time, and then optimizing this testing with this kind of equipment can give OEMs and their suppliers a distinct competitive advantage for meeting requirements of advanced vehicle systems. So as we get into the Q&A, if you need to sign off, I really do appreciate your time on the webinar today. And if you have any questions, please reach out to us at info@radiantvs.com. For those that are staying on, you could use the Q&A box to type and submit your questions, and I will try to get to as many as I can. Matt, do you want to go ahead and take over from here?
Absolutely. And thank you for that great presentation. We do have some questions that came in from the audience, so we're going to get to those in a moment. To the audience, as mentioned, if you haven't submitted your question yet, you can still do so now by entering it in the Q&A box and clicking submit. We have quite a few questions in the queue at this time, so we're going to try to get through as many as we can in the next 10 minutes or so. However, if we don't get to your question for whatever reason, we will reach out after the webinar is over. Okay, now for our first question from the audience. Aren't camera monitoring systems already allowed in U.S. vehicles for backup cameras? Brett?
Yeah, it's a great question. Yes, technically they are. So the one that we're kind of waiting on to become more legal is actually the rear view, or sorry, the side view mirrors. But as I mentioned before, everything that's been made, I believe it was May 1st, 2018, those are using camera monitoring systems as a backup camera.
Excellent, thank you for that. Okay, next question. Which mirrors are primarily being replaced in current vehicles?
That's a great question. So typically mirrors on the exterior sides of vehicles are being replaced for visibility and aerodynamic improvements. So these are the mirrors that are classes 1 through, I believe, 4 under ISO. The rear view mirror is more often being redesigned as a display or as an electronic mirror that can be changed from mirror to display state. So the display can provide a wider field of view with less glare, and there's a couple other benefits there, but yeah.
Very good, thank you for that. And thank you to the audience member that sent that in, and thank you to the audience member for all these questions that are arriving right now. Keep them coming. Like mentioned, we're going to try to get to as many as we can before we end the session today. Okay, here's our next question from the audience. When does the NHTSA regulation go into effect?
So this NHTSA regulation, no date has actually been announced, but there has been some reviewing going on and a lot of kind of notes and comments been passed around. It's something that, Radiant, we try to stay on top of. Of course, we're a part of a lot of these communities and a part of these meetings, and it's something that we kind of note when we release software packages or other solutions. We're trying to stay on top of that. But nothing has been actually officially announced at this time.
Excellent, thank you. So keep our eyes out for that one. Okay, and here's our next question. Are there specifications for things like general luminance, color gamut of the display?
Are there specifications for things like general luminance, color gamut of the display? So yeah, not all possible tests are covered by the standard, but we actually could do a lot more. We do have a lot of customers that essentially use our solutions to do more than what even the standard says. Because in a tier 1, a tier 2, or tier 3 might have a recommendation or requirement from the next tier or even the OEM to do like black mirror gradients, light leakage. All of those properties are also a part of the display that are typically tested. But absolutely, yeah. So there's other tests that can be done.
Excellent, thank you for that. And to the audience, we are in the Q&A session. You can send us your question or your comment. We would love to hear from you. You can add that information in the Q&A box on your screen and click submit. And while you're thinking of your questions, I just want to take a moment and point out on your screen in the top right corner, we have a lot of additional information that you can use to follow up with the Radiant Vision Systems team that's located in the resource list. Then across the bottom, there's a few buttons as well that you can engage with, and there's also a contact us widget on the bottom if you want to reach out. Okay, back to the questions. And here's our next question from the audience. How many cameras are necessary for testing the camera monitoring system display?
Just actually one colorimeter or one photometer is needed. Actually, it's a colorimeter because of the color rendering test. But one colorimeter is needed to perform testing that we reviewed today. But as I mentioned, there is some other test equipment that could be used, like there's let's say flickering, where we would use like a CA410 from Conoscopic. But there are different aspects to the test, but everything we covered today would just be one camera.
Excellent, thank you for that. And okay, we have a few more minutes, so we're going to keep it going here. So again, if you guys have any last questions or comments, now would probably be your last chance to send them in to us. And as mentioned, if we don't get to your question for whatever reason, we will reach out after the webinar is over. Okay, here's our next question. Are different systems needed to perform different tests of the display?
Great question, great question. So If you did not have a conoscopic lens, you could use a goniometric system, right? And that's the one that kind of rotates, whether it's rotating the display itself or it's rotating the camera. As I just mentioned in the last question too, like a CA410 for flicker, there are other components that could be used to really encompass all of this test and solution, but those are the main ones, be flicker in a goniometric system if a conoscopic lens was not available to the user.
Excellent, thank you. And another question on testing. I think you might have mentioned this, but I'm going to slide this one in anyway. And here it is. Can machine vision cameras be used for testing, or is a photometer required?
So a photometer is required. There are a couple specifications that call out luminance values and of course the color rendering. So machine vision will only provide a gray value. It's not going to provide a absolute candela per meter squared. Same with using the goniometric system or a conoscopic lens. It's only going to provide a gray level, and it does a reference test, which is not going to be able to follow that standard specified here that we've talked about today. So yeah, absolutely. You've got to use a photometer or something calibrated with candelas per meter squared.
Excellent, thank you. That was a great question. Thank you to the audience for sending that in. And here's another great one. What is the test procedure for displays that are shapes other than square or rectangle?
Good question, good question. Yeah, we are starting to see, of course, non-rectangular displays in the vehicle, or even curved displays, circular displays, you know, all kind of crazy shapes. What's important there is to have a image processing registration method. It's something at Radiant we actually specialize in. So we have a lot of customers that use, you know, the freeform registration method where all the outside pixels are ignored and only the active area is going to be calculated, which means that you can continue to follow these standards even with a non-rectangular display.
Very cool. Okay, and looks like we have time for one last question. So as mentioned, if we didn't get to your question for whatever reason, we will reach out at a later time. Okay, but for now, here's our last question for today's session. What kind of equipment is needed for the time-based testing? For example, frame rate, system latency, etc.
Yeah, good question. It's going to be a combination of a solution like an imaging colorimeter, a flicker meter, again, like a CA410 or equivalent, and a spectrometer. So it's going to be those three pieces of equipment to encompass the rest of the testing for frame rate, for system latency, and all of that.
Excellent. Thank you for that. And that was our last question. So we are going to wrap things up right there. So Brett, once again, thank you very much for taking the time to be with us today, and also taking the time to answer some questions from our audience. Absolutely. It's a pleasure. And of course, thank you to all of our audience members for being part of this webinar event. You will be receiving an email from us with a link to the on-demand version of this presentation, so you will be able to come back and watch this again or share it with your colleagues. And lastly, please take a moment to complete a survey which will appear on your screen at the end of this live webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you for taking the time to attend this webinar event. Take care, and we'll talk with you soon.